Quantum mechanics, where the cat is in a box, a particle is in a box, and this man is also in a box. Except they checked he was dead before they put him in that time. At least I hope they did. Did they? Yes. Okay, they did. What is quantum chemistry? Let's take a look. Basically, if you know any quantum, you know about wave-particle duality. If you don't, basically some guy called Young did an experiment where he found out that electrons acted like a wave. Which means this kind of orbital visual that people have developed for electrons is incorrect. But rather they occupy different wavelengths around a nucleus. Then Schrödinger, the cat guy from earlier, made this equation to determine what those wavelengths were. Because that's just horrible to look at, they used this instead, which is called the Hamiltonian equation, which combines potential and kinetic energy to find out the evolution of the wavelength, which lead to subshells, which look like this. Well, they don't look like this is how they're worked out. They look like this. Each one of them has a different shape because of the Hamiltonian equation. The evolution is the amount of energy given off when an electron moves further out into the cloud. And from there, it made sense that an electron had to be somewhere in a cloud around a nucleus. But this guy, who's not this guy, but is this guy, figured, well, you can't know a particle's position and speed at the same time. And this is called the Heisenberg uncertainty principle, which leads to something called entanglement. When you're doing electron subshells and you're doing your arrows, you're drawing the direction of the spin of the particle. And what that means is when you know the direction of one of the electrons, you know the direction of the other because they have to be in opposite spins. Which brings me on to quantum teleportation. But don't get too excited. It's not beam me up Scotty level of teleportation. Let's say you have two particles, but you don't know whether they're in state A or state B. Now you and your friend go to opposite ends of the globe, and one of you opens your box. When you find out you've got particle A, you know your friend has particle B. That's the principle of entanglement. But when you introduce state C to your state A, you create a different scenario. So particle A and particle C are now entangled. You then measure the state of particle A, and the data collected is sent but via, normal communication. Now the state of particle C is reconstructed on particle B, and so, what do you know? Particle C has teleported. And it's not cloning because there's something called the non-cloning theorem, which means that particle C will have been destroyed in the process. Moving on is density functional theorem, or DFT for short, which basically suggests that properties of materials can be decided from the electron density rather than the multi-wave function. I'm not going to explain it because it's awfully complicated. This is good though, as the many electron wave function requires 3 times the number of electron functions, whereas this one only needs 3. DFT relies on the 3 spatial measurements x, y, and z, so it makes it a lot easier to compute. Now the equation looks something like this, which is horrible, but don't forget it's for computers to do. And all of the letters you see are just different types of energy, and one of them is charge. That's really it. It looks bad, it's not that bad. If you want to read up more on it, I can highly suggest it. I didn't go into detail on it because I don't want to be here for the next 3 hours. And then comes the Kohn-Sham equation, aptly named because you basically make up particles with the same properties as your particles and use them to solve it iteratively. Again, I've got a life to live, so I'm not going to go into massive detail on this. Maybe in a quantum part 2. We'll see. Anyway, you know how I said electrons were waves? Let's take a closer look at that real quick. If you do A-level physics, you'll know that waves interact, and they either interact constructively, increasing the amplitude, or destructively, minimizing the amplitude. And this is based off two principles. The first one is that the lowest energy shells fill first. The second is that electrons occupy different shells before pairing up. So when two electrons with opposite spins interact, it causes something called antibonding, which you can see is signified with a sigma and then an asterisk. Which brings us to hybridization. Hybridization is how you get bond angles. So this is the interaction between an S shell and a P shell, and it forms a linear molecule. This is sp2, which is the interaction between an S shell and two P shells, which forms trigonal planar. And then you have sp3, which creates tetrahedral, and so on and so forth. That's going to be it for this week. Absolutely mind-boggling, and some really complicated maths to go with it. I hope you enjoyed. Please remember to like and subscribe, and I will see you next week when we're talking about soap. So I'll see you then. Bye.